Hello and welcome to this module about the Lighthouse project in RANCHI. My name is Sabine Giegelmeier and I'm Business Development Manager at the Fraunhofer Institute for Building Physics, IBP, in Germany. In this module, you have already learned some aspects of building physics for the construction project in RANCHI. This lecture will therefore once again deal with the building physics comfort assessment using this project as an example. Specifically, it will deal with the aspects of local thermal discomfort. For example, the radiation asymmetry and the vertical air temperature differences, what they are exactly, how they arise, and what effects they have on the comfort in an indoor climate. Therefore, let's get started. The last modules already discussed the concept of thermal comfort, how it is measured and influenced. On the basis of this, I would like to introduce you to the effect of radiant temperature asymmetry. This has a significant influence on the overall thermal comfort in a room. Radiation temperature asymmetry can be described as the interaction between the temperature of the ceilings or wall surface and the temperature of the human body surface. Radiation asymmetry is, for example, particularly pronounced with warm or cold ceilings and warm or cold walls. Delta TPR is the basic calculation variable for this. To visualize what this is, you have to imagine the room and divide it into two half rooms and their temperature, both in section horizontally and vertically. Delta T PR then results from the difference between these half-space radiation temperatures and the human surface temperature. Whether a ceiling is then perceived as too warm or too cold is determined when this difference in the radiant temperatures is inserted into the formula for determining the percentage of dissatisfied people. 4 different rates of thermal dissatisfaction can thus be determined. Warm ceilings and cold walls result in the most critical conditions for thermal comfort, as even small temperature differences lead to a high percentage of dissatisfied people. For example, the radiant temperature difference increases because the sun is shining on the roof. The energy can pass through the roof into the room, so that the air below the ceiling is heated by the sun. This temperature increase is perceptible in the whole room, but especially directly under the ceiling, the local air temperature will be significantly warmer. This leads us directly to another aspect that also leads to local thermal discomfort, the vertical air temperature differences. This is mainly influenced by the heating, cooling, and ventilation system. On the left, you can see the optimal temperature profile. This means that warmer temperatures are desired near the floor, and cooler temperatures are desired close to the ceiling. The different heating systems lead to very different air temperature profiles. For example, radiators, which are shown in 2 and 3, lead to an exactly opposite temperature profile than the ideal one on the left. That means it is colder on the floor and warmer on the ceiling. The heating system 7, underfloor heating, comes closest to the optimum, even though the optimum cannot be achieved with any system. Moving on to another related issue. Let's look at the impact of insulation on the roof and especially how it affects thermal comfort in the attic flat. When the sun is shining, we see that in an attic flat without insulation, there is a lot of energy through transmission. So the radiant energy penetrates into the room and thermal comfort is no longer guaranteed. The attic flat with insulation on the roof, on the other hand, reduces this transmission, since much of the thermal solar radiation is reflected and thus thermal comfort is still ensured. This can also be seen quite well in the vertical air temperature profiles already introduced. After simulating a RANCHI attic flat without insulation, we see temperatures near the head of up to 39 degrees. That degrees only slightly over the vertical distribution, except near the floor. The attic flat with insulation, however, manages not to let temperatures get above 37 degrees, with a relatively even decrease in temperatures down to the floor. Another interesting finding is the fact that with an uninsulated ceiling, the course of the day has a much greater influence on the temperature. In the morning, it is still cooler, and then rises sharply due to the heating up over the midday period, with the heating up continuing until the evening. Only at night, that means after sunset, it does cool down. The course of attic flat with an insulated ceiling is again much more constant. I would like to conclude with the definition of thermal comfort, which you are already familiar with, in order to integrate the phenomena shown into the general topic. In general, thermal comfort can be described as follows. In the ASHRAE Standard 55, thermal comfort is defined as that condition of mind that expresses satisfaction with the thermal environment. Another definition says that the condition of thermal comfort is sometimes defined as a state in which there are no driving impulses to correct the environment by behavior. Whether a person finds the environmental conditions comfortable or not is subjective and different for each person. However, there are evaluation methods that make it possible to assess how many people will be satisfied or dissatisfied with a particular climate. Or from another point of view, which climate is perceived as comfortable or uncomfortable by the majority of the people. Various conditions have an influence on our perception of the indoor climate. Radiation asymmetry and vertical temperature differences are clearly part of this topic. And with that, I would like to say goodbye to this lecture. Thank you very much for your attention and see you next time. Goodbye.